Okay, good morning. We are going to get started. I do want to officially notify all of you that I am recording this Zoom call and we'll post it on YouTube this afternoon. So just be aware of that. A couple things I want to share before we dive into the lesson. I want to remind you of your test coming up on April 28th. That test will be an exam similar to what you took the other day. Online. You'll have a couple of chances to take it during that day. So just be aware of that. Another thing that I want to remind you of is your final exam coming up. I believe we said it was going to be on May 7th. That is the date that is sticking out in my head. I'm looking at my phone. Yep, May 7th, Thursday, May 7th will be that final exam. And again, that final exam will be a written exam that I will post in Canvas and you'll need to print out. Speaking of Canvas, I want to share with you the fact that I did go into Canvas and post your final exam review. So if you go to the Files menu in Canvas and just in the general section, not in the Zoom notes, but in the general section, if you scroll down, you'll see M100 final exam review questions. And if you click on that, it will open up a 14-page document. And these are just example problems for you to practice to prepare for your final. And I do want you to notice that the solutions are also there. The last 7 or 8 pages go into step-by-step solutions to those problems. I had to revise this document from previous semesters, and so if you catch any numbering issues, if I failed to number something correctly or whatever, let me know. But anyway, as I said, that document is in Canvas, and trying to close it out. I guess we'll just do this. It's in the Files section right there. So I encourage you to print that out. We will spend at least a couple of class sessions, and Chris will spend an SI session or two going over problems in that to prepare you for that final exam. So does anybody have any questions regarding your next test or your final exam? All right. I do want to remind you, and I know that we're all kind of locked down here and it seems like this online thing is going on forever, but we only have 3 weeks left. Okay, 3 weeks from today is that final exam. So be encouraged that we're getting through this, and there is a light at the end of the tunnel. So I think that hits everything that I needed to tell you in terms of announcements. Does anybody, I see a couple people have logged in the last minute or two. Does anybody have any questions regarding anything else before I get started with lesson 12.3? Okay, well, we're going to go ahead and get started then. I see Jason and Charles. Those are are the two people who are willing to show their faces, and I appreciate that because I at least feel like I'm looking at somebody. We're going to talk about section 12.3. I want to remind you that I did upload Zoom notes for section 12.3 into the Zoom notes folder in Canvas, and I am going to be referencing those notes. So I'm going to pull those up right now. Again, if you printed them out, then you would have them in front of you, but if not, this is the document that you're looking at. As a reminder, on Tuesday, we talked about different ways to count things. Okay, how do we count things that are more complex to figure out than simply counting 1, 2, 3, 4, 5, for example? And we talked about the fundamental counting principle. You'll remember, I hope, the idea of building a Subway sandwich and the number of different sandwiches that we can build by multiplying together the number of types of bread and the number of types of meat and cheese and all of those things, fundamental counting principle. We're going to be using that a little bit in section 12.3 as we begin talking about permutations and combinations. So I'm going to go ahead and reference that document that I've posted in the notes yesterday. And we're going to start by talking about permutations. Now, many of you may have not have heard the term permutations before. Combinations is something much more commonly known. I'm sure almost everybody, if not everybody in class, has had a combination lock, for example. When you're in high school, you had a locker and you had a combination and so forth. What's interesting is that the term combination and the term permutation actually have reverse meanings. So here's what I mean by that. Let's say that when you were in high school, you had a locker and the combination was 10, 20, 30, just to pick some easy numbers to remember. Well, if you had gone up to that locker and you had put in the numbers 20, 30, 10 or 30, 10, 20, it would not have opened, because we know that when we put a combination into a combination lock, we have to put it in order. But mathematically speaking, that actually is the reverse. So we're going to start by talking about permutations. And the most important thing for you to understand about permutations is that it's permutations where order matters. Okay, so actually you could say, you would never do this, but because it sounds hokey, but you didn't actually have a combination lock on your locker, you had a permutation lock, because the order in which you put in the numbers matters. Whereas in a combination, the order does not matter. And we'll talk about that in a little bit, okay? By the way, parenthetically, I want to remind you that if anybody has any questions, you need to go ahead and unmute yourself and say, Mr. Becker, I have a question. And the reason for that is because I am looking at the screen that you are seeing, and so I don't see the chat box right now, and I don't see any of your lovely faces. I just see this document. So please be aware that if you have a question, do not hesitate to interrupt me, and that is perfectly fine. We have to make allowances in this weird pandemic that we're dealing with. So anyway, back to the lesson. A permutation is the way that we order a number of objects, unique objects, okay? So for example, off the top of my head, there's about 7 or 8 of you in the classroom last time I looked. If I assigned seats in our class, think back to our class in room 332 at Hawthorne Hall, and if I assigned seats and there were 8 of you, how many different ways could I assign you 8 students into those seats? Okay, you're all unique or distinct. And if I put Jason in seat number 1, that would be different than putting Chuck in seat number 1 or putting Michaela in seat number 1 and so forth. So I want you to be aware that we're calculating an order of distinct objects where order matters. Okay, an arrangement of distinct objects where order matters. Now we use the letters N and R to help us understand for both permutations and combinations, which we'll talk about combinations later. Both N and R are letters that represent numbers in a problem. So for example, if we were to select R different objects from a set of N unique objects and arrange them in order, that's called a permutation of N objects taken R at a time. And this is the notation that we use for that. Okay. Now I know, excuse me, I know that we need some context to understand. So let's say that we have a permutation of 5 objects. We have 5 different things, taken 3 at a time. I apologize for my phone going off. Try and shut that off. All right. So we have 5 objects that we're selecting 3 of where order matters. Let's do an example. Let's say that we decide in our class that we're going to elect class officers, okay? We just have enjoyed our class so much that we've decided we're going to elect class officers to, act as advisors to the instructor or something like that. And so let's say that 5 of you have volunteered to step forward and run for 3 offices, okay? So out of all the students in our class, there's about 23 students who still remain in our class this semester. 5 of you step forward and say, I want to be a class officer, okay? Well, there's only 3 positions and there are 5 people willing to serve. How many different ways can those 5 people be chosen 3 at a time? Nobody's allowed to hold more than 1 office. So if you're president, you can't also be vice president. And if you're secretary, you can't be president as well, and so forth. So how many different ways can we fill these 3 unique positions from the 5 people who are willing to run for office? This is an example of a permutation. okay? So let's say that the 5 individuals are named Ahmad, Braden, Christine, David, and Eliza, okay? Now, these first 3 names are actually people in the class. I was going for something alphabetical because it's easier to understand. And I can't believe, but I actually found an image online of a t-shirt that says Ahmad for president. So I got a kick out of that. But anyway, so let's say that Ahmad, Braden, Christine, David, and Eliza are willing to run for office. We're going to use the letters A, B, C, D, and E for those 5 people. Now, if we were going to just try and list the number of different ways that those 5 people could fill 3 offices, it would take a long time. For example, let's try that systematic listing idea that we talked about in 12.1. Let's talk about that for a minute. So we're going to use the initials A, B, C, D, and E. The person whose initial comes first will be the president, second would be the vice president, and third is the secretary. So for example, there are 3 ways that Ahmad could be president and Braden could be vice president. Okay, Ahmad president, Braden vice president, and Christine could be the secretary, or Ahmad president, Braden vice president, and David could be the secretary, or Ahmad president, Braden vice president, and Eliza the secretary. So that's 3 ways just that Ahmad could be president and Braden could be vice president. There are also 3 ways where Ahmad could be president, Christine could be vice president, and then Braden could be the secretary, or David could be the secretary, or Eliza could be the secretary, and so on. We could continue that pattern, okay? And as you can imagine, this could get very cumbersome and very tiresome and very boring, okay? But there is a way to count the number of different outcomes or permutations. Remember, order matters. There is a way that we can count these permutations of 5 people selected 3 at a time. There's a formula, and formulas are always nice. They're not always pretty, but they're always nice. I want to remind you, if you think back to when we did the line of best fit in the early part of the semester, and we had that really horrific looking formula where we had sigma x and sigma y and sigma xy and all that stuff. And the formula looked ugly, but the nice thing is you can just plug some numbers into the formula and get results out. There is a formula, but before we talk about that formula, we need to understand another term, and that term is factorial notation. Factorial notation is a mathematical operation involving multiplication. And the easiest way for you to understand it is to simply jump into a very basic problem. So let's say that we want to arrange a group of 4 books on a shelf. Here's an image right here of 4 books, 1, 2, 3, 4 books on a shelf. How many different ways can we fill or order these 4 books on the shelf? So there are 4 positions, 1, 2, 3, 4 positions for us to put the books on the shelf. And we would have 4 different choices for what book to go first. Maybe you're putting them in order from your favorite book to your least favorite book. Or maybe you're putting them in order from highest book to tallest book to shortest book. Or maybe you're just randomly throwing them on the shelf. In any case, there are 4 positions that you're going to fill, or 4 slots on the shelf. And there are 4 book choices for the first position. So if we put this brown book here first, then there are 3 other books that could go second. If we chose this red book second, then there are 2 other books that could go third. We chose this kind of orangish book. Actually, I guess that's orange and that's more red. But anyway, there are 2 books that could go there, and then there's 1 book left to go there. Now, based on that fundamental counting principle that we talked about on Tuesday, we can say by filling slots that there are 4 times 3 times 2 times 1, which is a total of 24 ways to arrange the books on the shelf. The books are unique, okay? So we're finding a permutation of 4 books chosen 4 at a time, which is this notation right here. And of course, that's the same as 4 times 3 times 2 times 1, which we just looked at. Now, this can also be a very tedious process, because if you have really large numbers, like if you wanted to know the number of ways you could arrange 100 books on the shelf, you'd have to do 100 times 99 times 98 times 97, and it gets ridiculous, okay? So what we do is we use something called factorial notation, and the symbol for factorials is an exclamation point right there, Okay, that's the exclamation point for, which means factorial, which means that we're going to multiply a number times 1 less than the number and so forth. So in other words, if n is a counting number, and this is important, we're talking about numbers that you can count with, 1, 2, 3, 4, 5. We're not talking about 2.5 or 3.4. We're talking about counting numbers. They have to be positive, okay? So if we're talking about n factorial, what that means is that we multiply that number times 1 less than the number, times 2 less than the number, times 3 less than the number, all the way down to 3 times 2 times 1. And by the way, just as a definition, 0 factorial is equivalent to 1. Okay, put a box around that. So let's go ahead and take a look for a moment at example 2 over on page 639. So I'm going to share the textbook for those of you who might not have it. Hang on, I got to pull it up here. Okay, so back to share screen. Okay, so here's the textbook. That's page 637, 638, 639. Okay, so here we go. We're looking at factorial notation. Let me zoom in on that a little bit, not a lot. Okay. So factorial notation, example number 2. If we're asked to calculate 6 factorial, very simply, that means you're going to multiply 6 times each of its preceding numbers, walking it down one at a time, 6 times 5 times 4 times 3 times 2 times 1, and then you're going to get that solution. By the way, your calculators all have a factorial notation on it somewhere. Some of them are a little harder to find than others. On the on a graphing calculator, you might have to go into the probability menu. It might be right there on a TI-30 for you. But if anybody has any questions about how to find it, I'd be happy to walk you through that. So, order of operations is always applied when we're talking about factorial. So for example, this 8 minus 3 in parentheses factorial, you would do what's in the parentheses first. You do the 8 minus 3, which is 5, then apply the factorial. Because remember, parentheses is the first thing that you do in order of operations, and factorial is a multiplication operation. Okay, so you do the parentheses 8 minus 3, and then you walk that down to multiply it out and get 120. In letter C, when you have 9 factorial over 5 factorial, I want you to notice that you could write that out as 9 times 8 times 7 times 6. This part right here in red on top, 5, 4, 3, 2, 1, that's a 5 factorial. You wouldn't even have to write it out if you didn't want to. You could have just done 9 times 8 times 7 times 6 times 5 factorial and then canceled it with the bottom. And then you multiply those numbers together. Sometimes you're going to have multiple factorials in the denominator. This is particularly true when we get to combinations. And so what you need to do in the denominator is you need to, if you write out 8 times 7 times 6 times 5, 4, 3, 2, 1, you could have written this as 5 factorial, and this could have stayed 5 factorial on the bottom, and those would have canceled. So you'd have 8 times 7 times 6 over 3 times 2 times 1. Well, 3 times 2 times 1 is 6, so that will cancel the 6 in the numerator, and you just have 8 times 7 left. Now, one of the most important things for you to understand about factorial notation and dividing problems when you have factorials in the numerator and denominator is that your answer will always be an integer. You will not get decimal answers. You will not get fraction answers. You will always get a counting answer because you're finding the number of ways that something can occur. All right. You're counting something. And again, I know I said this, but I want to make sure you understand, you don't count something as 1, 2, 3, 3.5, 3 3/4, 4. It's 1, 2, 3, 4, 5, 6, 7. So your answer will always be a counting number. And if you get a number that is not a counting number for your answer, you have made a mistake. Very important for you to understand that. So let's go ahead back to the document for a moment. Okay, and this is going to lead us back to the formula for permutations. So I want to stop right there for a minute. Of course, in class, if I were giving this lecture, I could be seeing all of your faces and I could determine whether you are understanding or whether you have a question or anything like that. So I want to stop for a minute and ask if anybody has any questions. You can post it in the chat if you have a question, or you can unmute yourself. Anybody? So Chuck, did you find the factorial on your calculator?
I'm trying to find it. I think it might be right there where it says fix. So let me go 0. And I do fix. It just has F 1, 2, 3, 4, 5, 6, 7, 8, 9.
That is not your factorial. That is, I believe that is going to fix the number of decimal places that your solutions will have. Do you have a key on your calculator that says PROB or PRB? That would stand for probability.
Yeah.
Okay, if you click that, I believe based on the calculator, and of course the image was a little blurry for me to see, but based on that, I believe that if you click on that, it's going to give you the factorial, it's going to give you a combination and a permutation function that you can use. Does it show, if you push on that, does it show like 3 options?
It shows NPR and
NCR. Does it show an exclamation point at all?
At the end, yeah.
At the end, okay, so yeah, that's where you're going to access your factorial. So Chuck, what you would do is if you wanted to find 5, yeah, if you do like 5 factorial and then hit equals, it should tell you the answer. So you'd put in your number, you'd go to that PRB button, you'd hit the factorial, the exclamation point, and it should give you like 120 or whatever the answer is.
Oh, okay.
That work?
Yeah, that worked. It says it gave me 50, 40.
Okay, so that would probably be 7 factorial,
Mm-hmm.
I think, off the top of my head. Now the NPR and the NCR, those refer to permutations and combinations, Chuck, which we're going to talk about, so that's going to be useful for you. The notation on the calculator is a little different than the notation that we use in the book, but it's the same function. So I just want you to be aware of that. All right, excellent question. I hope that that helps you understand how to navigate that for your calculator. And by the way, folks, that's going to be very important on your next test and on your final, knowing how to find the permutations and the combinations on your calculator so you can check your work. So cool. Anybody else? All right. So we are going to go back now to the document. And here is the formula for permutations. Now, this is the notation that you're going to see. You're going to see this textbook uses P parentheses NR. And what that means is because it's the letter P, that identifies it as a permutation. When we get to combinations later on, I'll show you right there, there's the same formula with a C for combinations. It's actually not the same formula. It's slightly different. But this is how you denote whether you're doing a permutation or a combination. It's the letter P or C. So we would read this as the permutation of n objects taken R at a time. Okay? So the formula for that, the permutation of n choose R, another way to say it, is n factorial. In other words, that first number right there, factorial on top, divided by n minus R factorial. So let's go back to our class officer problem that we talked about a little bit earlier. Just as a reminder, we got 23 people in the class. 5 of you have volunteered to run for class office, and there are 3 offices to choose from. The question is, how many different ways can we elect a president, a vice president, and a secretary from those 5 people? And remember, we were looking at it and trying to just list, and it was pretty cumbersome. There's 3, we got 6 right there, and if we kept going, it would take a long time. But what if we just want to know the number of different ways that we could do that? Well, we're going to plug those into the formula. The formula up here, permutation of n choose R, is n factorial over n minus R factorial. So the n is 5, and the r is 3. So I'm going to plug those values in. So n factorial would be 5 factorial on top. On the bottom, we have 5 minus 3 factorial. So that's 5 factorial over 2 factorial. Now I've written it out entirely because I want to make sure everybody understands. 5 factorial is 5 times 4 times 3 times 2 times 1 over 2 factorial is 2 times 1. So hopefully you can all see that we can cancel the 2 times 1 there and the 2 times 1 there. Those will cancel each other out. I've highlighted them so that you can see that. And when they cancel each other out, you're left with 5 times 4 times 3, which is 60. Now, when we started listing up here the number of different ways that we could get 3 officers out of the 5, I'm sure none of you imagined that it would be as many as 60 different ways that we could elect a president, vice president, and secretary. So you can see it would have taken a long time. It would have been very difficult. We probably would have made mistakes along the way. Okay? So it's much easier to simply find out the number using the formula than it is by trying to list them all and count them out. All right? So this permutation formula is something that you're going to use on your test and on your final. Very important that you know how to do that. I just walked Chuck how to find that on your calculator. So Chuck, what you would do on your calculator, if you were going to find the permutation and you wanted to do the permutation of 5, choose 3, what you're going to do is you're going to put in the number 5, and then you're going to go to that probability button and hit that. And then on your calculator, the NPR, that's a different way of notating permutation of n choose r. So you're going to put in a 5, then you're going to hit the NPR key, and then you're going to put in a 3, and then you're going to hit equals, and you should get 60. Okay? So I would encourage you to give that a try just to make sure that it works. All right. So let's go ahead and take a look back to the book. We're going to go to example 3 on page 640. Find that. Page 640. Here we go. Counting ways to fill positions at a community theater. I must admit to you guys, and this will probably come as no shock to anybody, but community theater is near and dear to my heart. When I was in high school, I was in a number of plays and musicals, and I actually had the lead in a couple of shows. So I've always been a bit of a ham. So I really like this problem. So here it is. We've got 12 people in a community theater group, and they're going to put on a musical. So out of those 12 people, they need to select a director. They need to select someone to supervise the music and a third person to handle the business side, publicity, tickets, and so forth. In how many ways can they fill the group? Can the group fill these positions? It's important to understand that if you're being the director of the show, you're not also going to supervise the music, and you're not also going to handle publicity, okay, in this situation. So it's obviously order matters. If it were a vote, if you were voting and it was popularity, the highest number of votes would be the director, the second highest would be the music director, and so forth, okay? It's a permutation problem. It's the permutation of 12 people from which you're choosing 3, okay? So 12 factorial over 12 minus 3, remember n minus r is 12 minus 3, which is 9. Now the nice thing about this again is that 12 times 11 times 10 times, you could write this next part here as 9 factorial. You don't have to write the whole thing out if you don't want to. You could have just written 9 factorial on the top and 9 factorial on the bottom, and then easily cancel them out instead of doing it one for one. They're showing you every single step, but you could have just canceled 9 factorial over 9 factorial, and you're left with 12 times 11 times 10. And when you multiply that out, you get 1,320. That means there's over 1,300 different ways that they could choose a director, a musical director, and a business manager for this show. All right. So that's a nice example of a permutation. Let's go back to the document for a moment. Okay. So the next concept that we want to talk about is combinations. Okay. And so to help you understand a combination and the difference between a combination and a permutation, what I want to do is I want to tweak our class officer scenario a little bit. All right. Instead of selecting 3 of 5 people to fill specific positions, let's instead just pick 3 of them to form a committee. Let's say, for example, that instead of electing officers, we're going to pick 3 people to put together a class party, end of the semester class party, okay? It's a committee. It doesn't matter, for example, if we choose Ahmad, Braden, and Christine. It doesn't matter if we picked Ahmad, then Braden, then Christine, or if we picked Ahmad, then Christine, then Braden, or Braden, and then Ahmad, and then Christine, and so forth. The order is irrelevant. There's no hierarchy, if you will. There's no one who's in charge, and then a second in charge, and then a secretary. The order doesn't matter. And that's the key concept in combinations, is that order does not matter. And this is why it's important to understand that difference, because when we think about combinations, you know, I have a locker in the fitness center at IUN, and it's one of those combination locks where it's got 4 letters. You know, the dials have letters on them, and you can make words or random letters or whatever. Well, if I put the letters in the wrong order, that locker is not going to open, and we think of it as a combination lock, but it's really not, because order doesn't matter in combinations. Okay. Excuse me. Now, the nice thing about combinations, like permutations, is that there is a formula. But I want you to notice it's very similar to the permutation formula. It is not the same. Okay, if we go back up here to the permutation formula, permutation of n choose r is n factorial over n minus r factorial. The difference between those, let's see if I can get them on the same page. Yeah. The difference between this one up top and this one down here is that in a combination, we also divide by r factorial. There's no r factorial in the denominator of a permutation, but there is in the denominator of a combination. So that's the difference, okay? So we want to be aware of that when we have a combination of n objects chosen r at a time, we have the n factorial in the numerator, we have the n minus r factorial in the denominator, but we also have an r factorial in the denominator. What that does is that divides out repetition, okay? Because we know that ABC and ACB and BAC and BCA and CAB and CBA are all the same because order doesn't matter. This r factorial is going to divide out the repetition. So, applying that to the class committee problem, okay, excuse me, the combination of 5 choose 3, notice, and again, Chuck, on your calculator, that's going to be the NCR, okay, different notation, but it's the same concept. The combination of 5 objects chosen 3 at a time is going to be 5 factorial, that's my n, over r factorial, my r, 3, times in the denominator n minus r factorial. So we have 5 factorial over 3 factorial times 2 factorial. Now remember, I'm going to change the highlight color. Here we go. There we go. 3 times 2 times 1 will cancel out 3 times 2 times 1. Okay? Those will cancel each other out. Actually, what I did is, hang on a second. I see I did something a little different. What I did is I canceled out the 2 times 1 here. And it doesn't matter the order in which you do this. I canceled out the 2 times 1s like that, okay? So then I was left with 5 times 4 times 3 over 3 times 2 times 1. Of course, in the next step, I could cancel out the 3's like that. And now I'm left with 5 times 4 over 2 times 1. When I didn't cancel them out, of course, I had 5 times 4 times 3 is 60 over 3 times 2 times 1 is 6. 60 over 6 equals 10. If I had done, let me go back to what I did a second ago. If I canceled out the 3's and I had 5 times 4 over 2 times 1, that's 20 over 2, which is still 10. Doesn't matter. I could cancel this 2 with the 2 up there, with 2 in the 4, and I'd have 5 times 2 is 10. Again, it doesn't matter. But the bottom line is that if I were choosing a committee of 3 people from the 5 people that were willing to serve on that party committee, if you will, there's only 10 ways to do that. So when order doesn't matter, there are 10 different ways that you can select those 3 people. Recall that when order did matter in a permutation, there were 60 ways to fill those positions. All right. So, excuse me. Let's go over to example 6 on page 643 in the book. Page 641, 2, 3. Now, some of you may not be card players, and that's okay. But I'm sure that everybody here in the classroom has heard of the game of poker. Long story short, in a game of poker, there are hundreds of different variations of poker. But in a general game of poker, you're dealt 5 cards from a deck of 52, and you have to put together the best possible hand. That's it in a nutshell. So you've got 52 cards, and you're choosing 5 of them. Now, here's what's important to understand. Why is a poker hand an example of a combination instead of a permutation? Well, very simply, it's because the order in which you receive the cards doesn't matter, okay? So let me show you what I'm talking about here. Go back to the notes. So here's an image right here. This is, by the way, 2 pair. You've got 2 aces and 2 twos. The 9 doesn't fit in well with either of them. So this is a 5-card hand. It would be 2 pair. It's not a bad hand, but it's not one of the most powerful hands. But here's the thing. Excuse me. I think the cream in my coffee is clogging up my throat. Here's the thing. When you're dealt these 5 cards, it doesn't matter if they're dealt to you in this order, ace, ace, 2, 2, 9, or if you got the ace and then the 9 and then the twos and then the other ace, or the ace, a couple of twos and 9 and then the ace. It doesn't matter. You're going to end up with these same 5 cards regardless of the order in which they were dealt to you. Okay, so that is an example of a combination, because in the final analysis, the cards that you get are all the same regardless of the order in which they were dealt to you. So when we talk about dealing 5 cards from a poker hand, we're talking about a combination. So it's the combination of 52, choose 5. Again, this is your N. 52 is N. 5 is your R. So this is N factorial in the numerator. This is R factorial. And 52 minus 5 is 47 factorial. Now, they don't show you this. I wish they did. But if you were to write out the numerator, 52 factorial, and you walk it down, 52 times 51 times 50 times 49 times 48 times 47 factorial. You don't have to keep going 47, 46, 45. You could stop at 47 factorial, which is in the denominator, and then that 47 factorial on top is going to cancel with the 47 factorial on the bottom. So that's why they don't show it. They basically cut out a step here, and I'm not real happy that they did, but they eliminated a step. So the 47 factorials cancel, and on the bottom you're left with 5 factorial, which is 5 times 4 times 3 times 2 times 1. And now these numbers in the denominator can cancel with stuff in the numerator. So for example, this 5, they canceled the 5 with the 50, and it left a 10. Okay? They canceled the 4 with the 52. 4 goes into 52 13 times. That's where these numbers are coming from. The 3 goes into 51 17 times. So they canceled the 3 with the 51 and left you with 17. Of course, the 2 goes into 48 24 times. So now that you've canceled all these numbers in your denominator, you're left with the 13 times the 17 times the 10 times the 49 times the 24. And when you multiply that all out, you get 2,598,960, which means that there are over 2.5 million different 5-card hands that you can be dealt in poker. Now, Chuck, if you were doing this problem on that calculator of yours, you would put in the 52, then you'd go to your probability button, and when it comes up, you'd hit the NCR, then you'd hit 5 and hit equals, and it should come up with that solution right there. If it doesn't, let me know. Again, I apologize for my cough today. All right.
So will this help me win any poker games in the future?
Well, actually, that's a great question. And I will answer it this way. We didn't cover the probability section, okay, which is chapter 13, which is the next section. That's the section we're eliminating because of the interests of time, because of the coronavirus and everything. Having said that, if you were to take some time and invest in studying the probability section, understanding probability can help you win money at poker, because that's what a lot of professional poker players use. Yes, they're very good at reading people's faces and determining, based on people's reactions, whether they've got good cards. But it's also about understanding the probabilities involved. If you see the cards out on the table, for example, in Texas Hold'em, which is the most popular poker game going right now, if you see the cards out on the table and you know the cards in your hand, you can calculate in your head the probability. What's the probability that I'm going to get the next card that I need? And so you will find that a lot of professional poker players are actually experts at probability as well. So that's a long-winded way of answering your question, but yeah, if you wanted to do that, you certainly could study probability, and it would help you win money at poker. So, funny story, I'll make it very brief. Back when I was in high school, I was in marching band. I'm sure that surprises a lot of you. And so that Ahmad says that's why he took statistics in high school, so that he could win at poker, apparently. When I was in high school, I was in marching band, and we would go on these long trips. We'd travel around the Midwest and would be in buses for like hours on end. And so one of the guys was kind of a handy guy. He built a portable poker table with drawers in it to carry the cards and the chips and everything like that. And he built it so that it would fit perfectly on the seats in our bus, our school bus. And so we'd have 5 or 6 people that were kind of sitting around, gathered around, playing poker on a regular basis. And I figured out, one of my friends, whenever we played this card called Drop, that was the name of the poker. You were basically dealt three cards, and if you were going to keep them, we'd count 1, 2, 3, drop, and everybody who was dropped their cards was out, and everybody who was going to stay in stayed in. I had this friend who I figured out what's called a tell. For those of you who don't know what a tell is a physical reaction someone has that tells you what they're going to do. And my friend, every time he was going to drop his cards, he would put his hand on his chin, or his head on his chin like this. If he did this, what I'm doing right now, I knew he was going to drop his cards. And if he sat like this, I knew he was going to keep his cards. And I took him for quite a bit of money before I finally admitted. He was a friend, and we were playing nickel poker. So, I mean, it was, I took him for a few bucks, and then I told him what he was doing. But that's another way. That's why if you ever watch professional poker, you'll see some people who are wearing sunglasses, because sometimes your eyes will give away. Sometimes you'll get a twitch in your eyes, or you might raise your eyebrows or something like that. So you'll see people who wear sunglasses at indoors at poker tournaments, because they don't want to give away anything with their reaction. But anyway, so I know now not to play Ahmad in poker, because he studied it in high school and probably would take me for a good amount of money. All right, we've got one more concept. I appreciate you guys hanging in with me. It's a little smaller class today, and that's okay. Hopefully those who aren't here will tune into to my Zoom video that I post a little bit later. But I want to talk about one other type of problem that involves both permutations and combinations. I'm going to go back over to the textbook here, and I want to take a look at examples 7 and 8 on the next page. So let's go ahead and take a look at, whoops, here we go. Okay, so this is a nice problem. Let's try and give it a little context. The Division of Student Services at your school is selecting 2 men and 2 women to attend a leadership conference in Honolulu, Hawaii. Okay, so let's apply this to IUN, make it a little more personal. So we have a student services, Beth Tyler is the Dean of Students, and she's over all of the, student affairs and so forth. So let's say that she is getting ready to send 4 people from our campus, okay? 4 people, 2 men and 2 women, to attend a leadership conference in Hawaii. Now, I'm sure a lot of people would want to go. And so she puts out an email and says, hey, everybody, if you're interested in going to this conference in Hawaii, let me know. And she gets dozens and dozens and dozens of people who want to go, but only 10 men and 9 women actually have the qualifications. Only 10 male students and 9 female students are qualified to go to the conference. The question is, how many different ways can she decide what group to send? Now, let me point out, let's say that in our class, okay, let's say that Jason and Ahmad both are eligible to go. Now, Jason and Ahmad are not going to care what order they're picked in as long as they're picked. You know, if Jason is picked first and then Ahmad is picked second, or Ahmad is picked first and Jason is picked second, they don't care because they're both getting to go. So that means it's a combination. Okay, it's a combination of these guys. Same thing for the ladies. If Michaela and Judith, for example, are picked, they don't care whether Michaela's picked first and Judith second, or Judith first and Michaela second, because they both get to go. So it's a combination. Now, what's important to understand is that it's tempting to say, okay, we're selecting 4 people out of 19, so we're going to do the combination of 19 choose 4. That's actually not correct, because we've got 2 different categories of individuals. We've got men and women that have to be selected between. Because if we just do the combination of 19 choose 4, what if we chose 4 men? Or what if we chose 4 women? Or what if we chose 3 men and 1 woman, or 3 women and 1 man? Those are not acceptable choices, okay? So what we have to do is we have to break our group of 19 people into men and women and look at them individually. So we're going to choose 2 of the 9 women. And again, order doesn't matter. So it's the combination of 9 women choose 2. We're going to find that answer, which is 36. Then we're going to do the same thing with men. There are 10 men. We're going to choose 2. So it's the combination of 10 choose 2. We're going to find each of those independently. Okay, so there are 36 ways to choose the 2 women, and there are 45 ways to choose the 2 men. Now we have the numbers for the individual men and women, and we use the fundamental counting principle to find the total number of ways that they can be selected, because what you're really doing is you're filling 2 slots. You're selecting a men's group and a women's group. So you've got to fill the men's slot, and then you've got to fill the same slot for women, okay? So it's 2 tasks, selecting the men, selecting the women. Fundamental counting principle says that you would multiply those 2 numbers together, which we do at the bottom of the page. And we see that when we do that, we have 36 women times 45 men is 1,620 different ways that those two groups can be selected. Okay? So that's a nice combined counting methods problem. Let's look at one more on the next page, and then we'll be done. Same kind of idea, okay? So let's say that you and 15 of your friends have formed a company. Now, in this company, you're going to have a president, vice president, and then you're going to have a 3-member executive board, okay? Companies do this all the time. They have a group of people who are in charge. They elect the president and the vice president, and then they select a board of directors or something like that, okay? Well, it's important for you to understand that when you choose a president and a vice president, the order matters. That's a permutation right there, okay? Because the person who selected president cannot also be vice president and vice versa. But then the remaining 3 executive members can be chosen from, in any order, okay? So what you're going to do is you have to do it in 2 stages. Because the first stage is electing a president and vice president. There are 16 of you. Remember, it said you and 15 of your friends. So that's 16 people. And you're going to choose 2 of them. Order matters here because you're selecting a president and a vice president. Once you've chosen those 2 people, they are not eligible to be on the executive committee, the executive board. If you're the president or the vice president, you cannot also be on the executive board, okay? So that means that once you've chosen the president and the vice president, there are 14 people left that you can choose from. So it's going to be the permutation of 16 people choose 2. That's going to elect your president and vice president right there, okay? And then you're going to have a combination of 14 people choose 3. That's a combination because the order doesn't matter. And then you're doing 2 tasks. You're electing a president and a vice president, and then you're electing an executive board. So the fundamental accounting principle says that once you've found these 2 values, 16 choose 2 and 14 choose 3, you're going to multiply them together, and that will give you the total number of ways that your group of 16 people can elect a president and a vice president and then select a 3-person executive board. So again, we're combining strategies for counting in this problem. It's a nice problem. If you could do this problem, you should have no problem with any kind of counting problem on either of your remaining tests. And that, my friends, is permutations and combinations. I told you it was going to be a little bit of a shorter lesson today, and it was. Does anybody have any questions?
Okay, for
You
the
okay?
Go ahead, Christine, and then we'll
For
take
the-
Chuck.
okay, for the last problem you just did,
Yes.
The P would be the order. So because we had to pick, I mean, how does the order matter for the first one?
The order matters for the first one because you're electing a president and a vice president. They're different roles, okay? So the president is obviously a higher rank than the vice president. Contrast
Okay.
that with the second group, where they're just three members of a committee.
Equal
Nobody
people.
is.
Okay.
They're equal people, if you
Okay.
will. Okay, versus a president and a vice president. So, for
Gotcha.
example, if Ahmad were president and Braden were vice president, that's different than Braden being president and Ahmad being vice president.
True.
But over here, if Ahmad, Braden, and Christine are all selected to be on this committee, it doesn't matter the order in which it was chosen.
Gotcha.
Does that make sense?
Yes.
Cool.
Thank you.
All right. Chuck, did you have a question or a comment?
Yeah, the question was so if it would on the set before, if it would show the P for permutations, it would be NPR, right?
Yes.
Okay.
Yes. NPR on that kind of calculator is your permutations, and NCR is your combinations.
Mm-hmm.
And then there will also be a factorial. Now on your calculator, again, you're going to put in the N first, and then you're going to hit the NPR or the NCR, and then you'll put in the R number, and then you'll hit equals, and it should generate it for you.
Okay.
All right?
All right.
Cool. Anybody else have any questions? Okay. Again, I am going to post this on, I can't even think straight, on YouTube. I did not sleep well last night. I woke up at 8:30. I'm normally up much earlier than that, so I'm just not functioning as well as I normally would. What day is today? This is Thursday, right? Yeah.
Yeah.
I'm telling you, the days are just all running together for me. It's really ridiculous. So again, I want to wish you all good health. I hope that you're all staying safe, and hopefully we'll be through this all, fairly quickly. Hang in there, folks. We only have 3 weeks left, okay, of having to do this. And we're going to get through it. I really think, that if you just kind of keep focused and just one foot in front of the other. I'm saying this as much for myself as for you guys, because the only person in my house right now who is handling quarantine at all well is my wife. My wife is fine. She is happy as a clam. I'm starting to get a little stir crazy. I've got 4 kids at home who are starting to get a little stir crazy. And so hang in there. Oh, by the way, this is just informational. The government's talking about these stimulus checks that they're going to be sending out and stuff like that. I got mine, actually. So I had filed my taxes about a month and a half ago electronically, and yesterday in my checking account, this money from the government showed up. So I'm telling you that to let you know that if you have filed your taxes and you are eligible for that, it's coming, it's real. So, it's money to help us through the pandemic, I guess. And so if you're in that situation and you've got a stimulus check coming from the government, know that it is on its way. They are real. It's not something that the media made up. It's not fake news. It is on its way. So
I
having
didn't get
said
any.
that, you didn't get any? I'm
Yeah,
sorry.
in 2018, my parents claimed me as a dependent. So
Oh, bummer. Well,
yeah, that stinks.
yeah. Shame on them. Oh, those horrible parents. Anyway.
Well, they're not getting anything either because we actually made just in 2018 because we were doing so good. We were doing so good. Also, my dad took out his pension from the police department. They made just over what was the amount, the limited amount that you could make to get the check.
Gotcha.
So they didn't get anything either.
Gotcha.
And neither
I
did my
understand.
sister. She also got claimed as a dependent in 2018.
I understand.
So none of us
Well,
got any money.
Yeah. Well, we're trying to figure out how we're going to spend the money because the reality is, you know, it's a stimulus package to help stimulate the economy. So, you know, some people are going to hang on to the money because they need it to get, or, you know, to get through, and that's fine. But I'm still working. You know, I'm here with you guys. My wife is a government employee and she is still being paid, even though she's working, you know, has to stay at home. So I feel responsible, since I'm still getting my paycheck, to put money back into the economy. So we're going to do that. We're going to spend that money in a way that can hopefully help some other people. But I just want to let you all know that that money is real and it is coming. It may affect you. It may not affect you. It might affect your family. But we're living in a weird time, folks. But I want to remind you, this is just a blip in time. Life is going to return to normal, whatever normal might look like. It might be a new normal, but we're going to get back to our regular society eventually. Just hang in there and be smart. Don't be going out and doing crazy stuff and hanging out with all sorts of people and spreading the disease right now. All right. Okay, folks, you guys have a great weekend. I look forward to seeing you all on Tuesday. We will be starting chapter 14, which is statistics. Okay, we'll be starting statistics on Tuesday. All right. So that's all I have. I will see you guys next week and have a great weekend.